Hi, the chapter 7, the analysis of variance and the classical Wallis test. So in short, the chapter 7 have the categorical the predictors rather than continuous predictors. So chapter 6, we have continuous y and continuous x. And chapter 11, we have the same, but we have multiple predictors. We have the two or more factors, variables to explain y. And chapter 7, the y is still continuous, but the x is categorical. For example, we give the fertilizer to some plants, and the sample unit is the plant, and the fertilizer is a factor. So we have the fertilizer A, B, C, D, or maybe no fertilizer. So such variable is so-called categorical variable. So we consider the categorical x in chapter 7. Chapter 12 is mixed case, so they're more complicated than 6, 7, and 11. And actually, the categorical variable, then we can always think about the indicator function for categories. So if we have fertilizer, no fertilizer, fertilizer A, B, C, D, if we think about the indicator function of A, so that means the 0 if not A is not given, and 1 if A is given. So if we think about this, then this is just one special case of continuous numeric predictor. So actually, chapter 7 is a special case of chapter 11. So we don't really have to study in some sense, but we have some terminologies. And also, since we haven't studied chapter 11, it's good to study at first chapter 7. It's more concrete examples than the chapter 11. Okay, so references. We have several reference books, and most books have the chapters corresponding to this chapter. So you can see this chapter 11 in the Michael Croway's book, or chapter 16 in Julian Faraway's book. So this is in our website, so on Quran website, so it's free. The first one also you can find for free. And the last one, actually this one also you can find it for free. Yeah, so the first model, the one-way analysis of variance. So the one-way analysis of variance is a test to compare the two or more groups under the same assumptions as the equal variance two-sample t-test. So two-sample t-test, that we have only two groups, but the ANOVA, we can compare two or more groups. So it includes the t-test, but we can compare the three groups. So fertilizer ABC, overall, do we have any difference between these three or not? So we can test that hypothesis in one-way analysis by one-way analysis of variance. So one way is that we have only one factor. So if we have the two factors, such as the fertilizer and location of the plants, then we have the two factors. Yeah, so if only two groups, it's equivalent to equal variance, the two-sample t-test. So we have we can test multiple groups, but we have slightly stronger assumption that all groups have the same variance. Okay, so what's the model? So one-way one-way layout. So one-way layout assumes that the observations x sub ij, I is from 1 to L. So this is the number of groups. L is number of groups. And the j is equal to 1 to ni. I mean, number of groups, number of subsets, not really a group in the algebraic sense. And j is the 1 to ni. So ni is the number of observations in ice group. Number of observations in ice group. Okay, then our model is xij is equal to alpha I plus epsilon ij. So here alpha I is a constant, and epsilon sub ij is normal 0 sigma square, and this is independent and identically distributed. So that means the ice group has its own level, alpha I. So that is the average level for the ith group, but each observation have some randomness. So individual observation have some noise. So we have epsilon ij, but this has mean 0. And sigma square is the same for all group, all i's. Yeah, so this is the model. So in some sense, the alpha I, in terms of linear regression, so suppose that we only have the two groups, and then, yeah, so alpha 1 is kind of the indicator function for first group, indicator function for the first group, and also that we have the indicator function of second group. Then we have the epsilon ij. So this is the graph. This is the model, one-way layout. And one-way ANOVA the tests this hypothesis. So all alpha i's are the same. Against the sum alpha I and alpha j are different. Yeah, so probabilistic view. So alpha i's are parameter. So maybe in the previous one, if I1 is the indicator function for the first group, then alpha 1 is the coefficient for this indicator function, and alpha 2 is the coefficient for the indicator function for the second group. So here, the alpha I and alpha 2 are parameters, and random factor is epsilon. So xij is also random. So alpha I is a parameter constant. Epsilon I, maybe epsilon ij is random variable, and the xij is random variable also. And we define several quantities. And first one is x bar I. This is the group, the sample mean for the ith group. So this is the 1 over ni times summation of xij over all j's. J is equal to 1 to ni. And x bar dot, this is overall average. So actually, okay, so the take summation for all ij's, then divide by n. So entire average. So not the average of x bar I, but the just average of all xij. And here capital N is the total sample size. So n1 and n sub 1, n sub 2 up to n sub L, with the summation of that is capital N. Okay, so we define. So these notations are pretty convenient. Okay, and now the theorem to test the null hypothesis that discussed in the previous slide. So we define the sum of squared residual within groups and the sum of squared residual squared deviation between the groups, and also total. So at first, the sum of the squared deviation, the within groups. So within groups, so we have xi. So we have the 3 groups, for example. So the group I and the I is equal to 1, 2, 3, and this is the x value. Then group 1 have some observations, and group 2 have some observations, and group 3 have some observations, maybe here. So its mean is around here, here, and here. So within sample that we want to calculate the variability. So xij minus x bar I, xi bar. So this is for each group that we take the deviation. So we take the distance between observation and the center. Then take summation. So this is the sum of squared deviation within group. So this is basically the variability within group. And then we take summation over I is equal to 1, 2, 3. And the sum of squared deviation between groups. So this is basically the variability among these 3 levels. So we have this point and this point and this point. So this is the variability between these 3 groups. And that is defined by the overall average. The overall average is probably around here, x bar. So we think about the variability in these 3 observations. So that is actually this quantity. And yeah, so basically we have to take summation over I of xi bar minus x dot bar. X dot bar is here. But we also have the summation over j because we want to put the more weight if we have more observations. Okay, so in this example, we have 4 observations. But for example, suppose group 2 have 6 observations. Then we should put more weight on this observation. So that's why that we put the ni. We would like to put the sample size, the n sub I here. But it can be also written as the summation j is equal to 1 to ni. Anyway, the j does not appear in this term. So this means just ni times. And sum of squared deviation total is equal to this. So this is just the distance between each observation, each the crosses, each black cross, and the entire overall mean, the x bar dot. Then take summation over all ij. So that is the sum of squared deviation total. And you can prove that the sum of squared deviation total is equal to SSD sub w and SSD sub b. So this is the somewhat the simple algebra. Still, that we have to go through the calculation, and it takes several lines. But just use the definition of x bar dot and the x bar I, then you can prove this. And the point is that if these groups are different, if this group have the different means, so these group means are different, then SS between is larger and the SS within is smaller, relatively smaller. So if groups are different, if group means are different, so this quantity, the SS between is large and SS within is small. So if we take the ratio of these 2 quantities, then we can use that quantity as a test statistic. So that is the idea. And actually the definition of this F statistic is basically the SSD between and SSD within. But since we have we need some adjustments, that we divide this by the L minus 1 and SSB by L minus 1. Then SSDW by N minus L. So it's a little bit difficult to distinguish 1 and L. So just careful, N minus L and the L minus 1, L minus 1. Okay. Then this follows the F distribution with degrees of freedom L minus 1, the numerator degrees of freedom L minus 1, and denominator degrees of freedom the N minus L. So we can use this statistic to test. So we have seen that the large, so if group means are different, then SSB is large and SSW is small, so F is large. So large F, the reject null hypothesis of alpha 1 to alpha L are the same. So that means if the F distribution has the positive support and the skewed to the right, so like this. So we have some threshold. So suppose this is alpha, for example, 0.05. Then if the test statistic falls in this range, we reject null hypothesis. So this is the rejection region of H naught. So F is large enough, then we reject null hypothesis. And F follows F distribution. And F distribution is basically centered at 1. So it's asymmetric. So the center is a kind of vague word, but okay, so this is around 1. So center is 1. So if f is much larger than 1, then usually we reject null hypothesis. So this is the overall theory. So here that we have some terminology. The SSDW stands for sum of squared deviation within groups, and B is between. And the MS is mean squared deviation. So that we divide the SSB and SSW by degrees of freedom. Yeah, and the reject null hypothesis if the F is larger than some threshold value for F. Yes, so this is how to test the null hypothesis in one-way layout.